The goal of today's lesson is to be able to distinguish between linear and nonlinear functions. We have already worked with linear functions in the beginning of the year, and we remember how they have a constant rate of change, which would be the change in y over the change in x. They have a slope and a y-intercept. They could be expressed in slope-intercept form as y equals mx plus b. And another really important feature of these linear equations is that x is raised to the first power. So we would refer to this as a first degree equation. And I have shown a chart here that demonstrates linear functions where we have a change in y, so each time we are adding a consistent 2 to each of the previous terms, over the change in x, and each time we are adding a consistent 1. So if we are trying to look at our rate of change r, it would be equal to our change in y, which is positive 2 each time, over our change in x, which is a positive 1 each time. The rate of change would come out to be a positive 2. That's your slope. However, not all functions behave that way. We have many nonlinear functions, and to provide you with a few examples, we have quadratic functions that we studied this year. And these take on a different form. Standard form of those would be y equals ax squared plus bx plus c, where you have a second degree equation, since the highest exponent is now x squared. And then we have also been introduced to the idea of a polynomial function, in which you might have a cubic function, or you might have a fourth degree function. A cubic function would have the highest exponent would be x cubed, and if we have the highest degree of 4, that would be x to the fourth power. There are so many other types of functions that exist in algebra. We have rational functions, we have radical functions, we have trigonometric functions. However, for the purpose of this lesson, we're going to focus on one specific form, which is another nonlinear function, an exponential function. An exponential function is a function in which x appears as an exponent in the equation. So some examples of this would be y is equal to 4 to the x power. Now this is much different than y equals x to the fourth power. That would be a polynomial function, a fourth degree function. However, in this case, we have x as the exponent, making this an exponential function. We are taking 4 as the base and raising it to the x power. Another example of this would be y is equal to 1/8 to the x power. We're still using x as the exponent, but we're changing the base that we're using, in this case, to be a fraction. Both of these situations are exponential functions. One of the most basic exponential functions would be y is equal to 2 to the x power. Let's take a look at a table that matches that equation. Let's consider x to be 0. Then y would equal 2 to the 0th power, and y would equal 1 in that case. If we consider x to be 1, 2 would be raised to the first power, which would equal 2. If we consider x to be a 2, we would take 2 and raise it to the second power, and that would come out to be 4. If we consider x to be 3, we would take 2 as our base and raise it to the third power, and that would be 8. And what we're noticing is that we do not have a constant rate of change, but instead, each time the output is doubling. Whenever you have a situation where your x values are growing steadily, but your output is doubling, you have an exponential function. Another basic case of an exponential function would be if we had y is equal to 3 to the x power. This is still an exponential function because x is used as the exponent. And if we wanted to create a chart, we could do that. Let's consider using 0, 1, 2, and 3 for the x values. If x is 0, the y would be 3 to the 0th power, which is equal to 1. If x is 1, it would be 3 to the first power, which is 3. If x is 2, it would be 3 squared, which is a 9. If x is 3, it would be 3 cubed as the output, which is 27. And what you notice in this case is that our x values, our input, increases steadily still, but our output values are rapidly growing. They triple each time. The output is tripling. So just as in the case of the output doubling, when you have an output that is tripling, you have another case of an exponential function. Those are both situations of exponential growth. You're either doubling each time or tripling your output each time. So in both of those cases, I would label these as exponential growth. However, there are also exponential decay functions. Such as in the case of this equation, y is equal to 1/2 to the x power. Now we could set up a table of values to match this. And we could look at those same x values, 0, 1, 2, and 3. If x is 0, then y would equal 1/2 to the 0 power, and anything raised to the 0 power equals 1. If x is 1, we would take 1/2 and raise it to the first power, which would be a 1/2. If x is 2, we would take the 1/2 base and raise it to the second power, and this would equal 1/2 squared is 1/2 times 1/2, or 1/4. If we take the base of 1/2 and raise it to the third power when x is 3, this would be the same as 1/2 times 1/2 times 1/2, which would be 1/8. And now what we're noticing is that yes, your x values still grow steadily, but your y values are halving each time. You take 1, halve that to get 1/2. You take half of that to get 1/4. You take half of that to get 1/8. So now our output values are halving. Another case of an exponential function, however, the output values are decreasing, so that would be an exponential decay situation.